So before we really understand plant nutrition and how fertilizer nutrients work, we really have to understand what CEC is. Everybody see that on a soil test you get back? You got a big long column that says CEC. That stands for cation exchange capacity. That's a big fancy term for negativity. It's how much negative charge your soil holds. So every piece of dirt that all of us farm carries a net negative charge. Okay, and that's important because we have positively charged nutrients out here. And so you can take a positively charged nutrient and you can stick it to a negative side on soil. I bet if we went right outside of here, we're probably looking at 25 to 30 in places. The difference in those numbers is the amount of negativity that each one of those soils contains. So you kind of think about them like a parking lot. You know, a 25 to 30 CEC is going to have a parking lot that looks like Busch Stadium. You know, you have all these spots to put all these positively charged nutrients and attach them. It's like picking up pieces of metal with a magnet. It's the same kind of action. You go into lighter soils, timber soils, white soils, those CEC numbers get into the single digits. It's like the parking lot right out here. We can only fit so many of those pieces of nutrition into a spot. That's why it's really hard to build potassium levels, because potassium is K and it carries a positive charge. It's really hard to build those up to high levels on light soils. You just don't have enough spots to fit them. But one of the most important things about CEC is how it grabs onto this nutrient right here. That's called ammonia. So when you go put on gas, anhydrous ammonia, it reacts with water, it turns into ammonia. Ammonium nitrogen. Difference between ammonia and ammonium. Ammonium carries this positive charge. You can stick that to the soil and it's held very tightly. It doesn't go anywhere. The problem with it is that all ammonium nitrogen eventually ends up as this other form called nitrate. Okay, we got ammonium that's positively charged. Nitrate carries a negative charge. See, your soil's negative, nitrate's negative. Anybody got a fancy guess how well they stick together? Not worth a darn. Nitrate is constantly repelled off of the soil. It's pushed away. It'd be like putting two magnets together. It's not going to work. And so once your nitrogen moves into nitrate, you're sitting in a volatile place because we can lose it. We'll talk about that. But two big differences between the two fertilizers other than their charge is the plant can store nitrate nitrogen in its tissue. So if you have a neighbor that's all 28% up front, they broadcast 28 and work it in, say 200 units, I guarantee you that field is going to be greener and when it's probably, 2 foot high than the field with anhydrous ammonia. 28 has a lot of nitrate in it right off the bat and it can store it. The plant can only use ammonium nitrogen on an as-needed basis. So the plant calls for a protein to grow, it takes in ammonium nitrogen, and that's how it uses it. It can't store it. So we have a stable form up here, is ammonium, and we got our volatile form down here. So when we're talking about nitrate, we can lose nitrate nitrogen in two different ways. First one being called leaching. So since you have a nitrogen particle, molecule, whatever you want to call it, that's negatively charged and it can't ever attach to the soil, it's going to stay away. It's going to be in solution. It's pushed off. The big issue with it is it dissolves very easily in water. So what do you think is going to happen if you have a whole bunch of negatively charged nitrogen that dissolves in water after a 6-inch rain? It's going to carry it. It physically moves with the water and it carries it down into your tile lines. If you have sandy soils, this can happen in an inch or two rain because of the permeability of the soil. We call that leaching. The second way we lose nitrogen is through what's called denitrification. So nitrate dissolves easily in water, but it has 3 oxygens with it. So when we have extended saturation, so take last June for example, early June, when the ground was wet for 3 weeks probably straight. When you're saturated and you can see the ground is shiny on top, all of the pore spaces that used to contain air are now full of water. There's no air in the ground. It's completely gone. Well, soil microbes like earthworms and bacteria and fungi, they need oxygen to survive. And so what they do is they look for any kind of dissolved oxygen. You know, we have it right here. We got nitrate that's dissolved and it has oxygen. So the microbes actually steal an oxygen off of there to breathe. That causes the nitrate to get really volatile and it turns into a gas and it blows off. That's why the wet holes constantly show nitrogen loss, is because you're blowing the nitrate back off to the ground. So 2 different ways we can lose it there. I always put this up here because I think people think that just because we put on nitrogen fertilizer that it's all the same stuff. When in reality, 28 is much different than anhydrous ammonia. So when we put on anhydrous ammonia, we have our NH3. You guys have probably seen that on the scale tickets because none of us want to write anhydrous ammonia and get carpal tunnel. I mean, we just abbreviate it, NH3. So the 3 is important because we got to have water, got to have soil moisture when we put anhydrous on, right? Or else it's going to blow back out of the trench. You have to have water because you take one of the waters from H2O, water, and you stick it right here. And you form all 100% ammonical nitrogen, ammonium nitrogen. 28, on the other hand, which is down here, is a blend of urea, ammonium nitrate, and water. And so when all those reactions are done with 28%, you yield 70% ammonium nitrogen, but 30% of that's nitrate probably 2 days after you put it on. So, you know, we get a little bit nervous when people are using 28% all up front. We get nervous in wet years. And the reason for that is, let's just say, you guys got to remember I'm from Beardstown, so I'm going to use really round numbers when I do math. So if we have 200 units that we're targeting on field, and we're using UAN 28%, and we're laying that all down ahead of the planter and working it in, 60 units of that nitrogen is leachable and denitrifiable within 2 days after we put it on. I mean, you're sitting out there with a lot of your nitrogen that's vulnerable the day you apply. So the crop doesn't use a lot of nitrogen until it gets to be about waist, chest high. Those 60 units of nitrogen probably aren't going to be hanging around by that point. You're putting those out there in a very vulnerable state too early in the crop's life cycle before it can really use a lot of them. Whereas anhydrous ammonia is going to have to convert. So that's one of the reasons why we can't use 28 in the fall. It's because it won't hang around long enough. It gets even a little bit more complicated than this. So every fertilizer has different ratios of ammonium and nitrate nitrogen, but what is ammonium nitrogen, our stable form, some fertilizers will convert quicker to nitrate than others. So anhydrous ammonia, since it's a really violent reaction in the soil and we put it on in a band, it takes about 3 to 8 weeks to get to nitrate. That's the longest. It has the most longevity in the stable form of any other nitrogen fertilizer we use. That's why it works so well in the fall, and that's why anhydrous ammonia typically favors over 28% in wet years, is because it's going to stay in ammonium form the longest. So when you look at urea, say you're broadcasting urea ahead of time, it's going to get to nitrate in about 2 weeks, roughly. You know, about half the time anhydrous ammonia will. You're putting on 28 down here, you know, because it's that ratio of ammonium nitrate and urea, you know, most all that's going to be in nitrate within about a week and a half to 2 weeks. The other thing to remember is that DAP, or AMS, it gets to nitrate in 1 to 2 weeks. So when we put on DAP in the fall, and we're putting it on in a warm fall like this year, it's in the nitrate form in 1 to 2 weeks. You get 6 inches of rain around Christmas in places. You know, all that stuff's converted and it's gone. The kicker with DAP is versus anhydrous ammonia. We usually put N-Serve on. Bill, 99, 100% ammonium fall goes out, N-Serve out of here? Yeah. Yep. So N-Serve basically kills all the bacteria that take your ammonium and push it over to nitrate. So it's a shield around there. They make sure that no bacteria is going to convert that ammonium. Problem is it's got a time clock with it. It's only going to work for about 60 to 90 days at a 55-degree soil temp. So lots of questions about how's our fall nitrogen? You know, are we still okay because it was warm? You know, we had a warm, I think it was a record warm December, I think, or close to it. And one of the record wettest Novembers, I believe. So where are we at? If you just kind of do simple longhand math and you don't use a nitrogen model or some kind of predictive service, you can just start counting 3 to 8 weeks that it's going to take to convert to nitrate, and I got 60 to 90 days with my N-Serve. I feel really good about those numbers. Myself, personally, I don't think we've lost hardly any of our anhydrous ammonia. It just was not long enough. We weren't warm long enough by the time we got all the water at the end of December. Heck, I mean, we finished gas the 20th of November. You know, there's some models out there showing people losing 70 to 80 pounds of their anhydrous ammonia when that rain came through on Christmas. That's not accurate. There's no way. There's no way that could have happened based off of what we know about nitrogen fertilizer. We have lost nitrogen. And there's no doubt that we have. I think we lost a lot of that. And I think we lost probably some mineralized nitrogen, which we'll talk about here in a little bit. The caveat to that we haven't lost any nitrogen statement is this clock ticks when we get into these temperatures. So we are converting nitrogen as we go along. We have not lost any yet, I don't believe, of our anhydrous ammonia. Our potential for loss is high. That's what really bugs me about some of these nitrogen models and predictive services. They're scaring everybody into saying you lost a bunch of nitrogen. Well, you haven't yet, because nitrogen isn't lost in December, and it's not lost in January. We lose nitrogen in May and June when we get wet, when all of our ammonium is converted to nitrate and we get wet. So the difference in years are we're going to go into our spring with more of our nitrogen probably in the nitrate form than we would have liked. We would have liked for more of it to stay in the ammonium form. And so we can't begin to make disaster plans to side dress every acre until we see what happens in March, April, and May. We don't know yet. We know our loss potential is higher, but if El Nino keeps chugging along here and we stay dry, we're going to be just fine. I don't see any issues. It's the Illinois Fertilizer and Chemical Association. And they kind of co-brand an effort called NREC and NWatch. If Ed's in the room, Ed Corrigan is a member of NREC. He sits on the board there, and they do a lot of work with research on trying to figure out, should the government regulate us when we put nitrogen on or not? And should they regulate us on how much? So NREC is funded by do we call it a fertilizer fee, Bill? Is it a tax or a fee? Fee. It's a fee. So a fee that you see when you get a fertilizer bill, that goes to fund the NREC and NWatch programs. It doesn't look great on paper, guys, but this organization is doing wonderful things for the state of Illinois' agriculture. Gene Payne's the president of the IFCA, and like I said, Ed sits on the board. And they have stacks of data right now that show how in Illinois fall nitrogen is a really good thing. They're actually seeing higher levels of nitrate bleeding off from spring applications on poor soils than they see on fall. So we have a book. We're not regulated here in the state of Illinois because of this organization. It's kind of a funny thing, but as bad as Illinois is with debt and governors that went to prison and everything. We're like the worst state in the world to live in, I think still, which is something to hang your hat on. We are probably the shining star in regulations for agriculture. And that's kind of funny to think about. Ohio is now mandated and regulated. You can get arrested if you apply fertilizer on frozen ground and fined. I don't know if all of you have heard about what's going on in Des Moines, but the city of Des Moines had high nitrate levels, and they are suing the drainage districts upstream of their municipal water source. I'm a part of a drainage district where I live in Beardstown. There's not very much money there. I mean, you got much money to buy a tank of fuel for a pump. So this is how ludicrous, exaggerated all this is getting. But here in the state of Illinois, we don't have any negative press. We're doing really good. Now, we got some nitrates spiking in some lakes, and we'll talk about it a little bit. But for the most part, we are the shining star in ag for nutrient regulations. Big explanation to a simple slide here. But NREC went out and they did some sampling. And they have a fellow they fund, his name's Dan Schaefer, and he does a lot of the nitrogen work. He's an old retail guy. He used to come from FS, so he knows fertilizer. They went out and sampled some sites here. Okay, this was in eastern Illinois, but they had 8 sites that had about 163 pounds of nitrogen as anhydrous ammonia put on in between the 5th to the 13th of November, about the time all of us were running. Okay, so they sampled it on December the 7th and January the 5th. And out of 163 pounds, they still found they had 165 when they sampled it the first part of December, and 168 pounds when they sampled it the first part of January. The real key about this January 5th sampling date is, that was a week or so after we got the 3 and 4 inch Christmas rains. They shouldn't have found that much nitrogen if we had lost it. So it's there. Here's the issue, and what I said, why our potential for loss is high. This is how much nitrate nitrogen they're finding, and this is how much ammonical nitrogen they're finding. We would like those bars to be inversed. We would rather be seeing a lot more, and hopefully you all agree after that 10-minute dissertation, you'd like to be seeing more ammonical nitrogen, stable nitrogen. We are finding that more nitrogen has converted to nitrate than we would have liked. It's still there, but our potential for loss is high. That's the moral of this whole talk. I told you we were going to talk about mineralized nitrogen. We have lost nitrogen. We've lost mineralized N and we've lost DAP nitrogen. That's what they're finding in the lakes. We're getting some kind of nasty grams from Lake Springfield and Lake Decatur because their nitrate levels have spiked. A lot of this came from what's known as mineralized nitrogen. And so organic matter, this wonderful thing that you have in your soil that makes it black, has an ability to release a significant amount of nitrogen. So around here, you guys are 3-4% organic matter on most soils. You know, that level of organic matter has the ability to release 20 to upwards of 100 pounds of nitrogen back to the soil. We call that mineralized nitrogen, natural release of N. And the reason there's a range there is because it's kind of indicative upon the weather. What isn't in agriculture, I guess. That's the high road and everything. But mineralization peaks when your residue gets broken down, you have very mild temperatures with seasonal rainfall. So not too hot, not too dry, not too wet. Sorry, not too hot, not too cool, not too wet, not too dry. So 2014 was the prime example of a peak mineralization year. I mean, some of you guys are raising 300 bushel corn on 180 units of nitrogen. You know, there's no way you could have done that without the soil supplying a big charge of N to you. So that's what happened in 2014. We had natural release. The caveat to that is, as you move into timber soils or sands, there's nothing there. I mean, you go up into Mason County or Cass, some organic matters are 0.5%, 0.75%. You might get 15 pounds of nitrogen versus 100 naturally released up here on the prairie. That's the reason the ranges. And I put this up here. McLean County had a really good corn growing year. They had a lot better weather than we did. We got a research farm up in Lexington, and old Dan Fraley, he operates that for us. He's got a nitrogen trial here. What I want to focus on is this 125 pounds of N. Dan only put on 125 pounds of N and raised 260 bushel corn after beans. That's mineralized nitrogen. They just had a whole lot better growing environment than we did, and that dirt, I mean, you just want to scoop it up and eat it. It looks so good. I mean, it's black and friable. It is good stuff. So when you think about mineralization, it's heat, moisture, and residue dependent. It's one of the best falls I think a lot of us have ever seen. I mean, we started picking, and then we finished. And there was no breaks in between. We were hot and dry, and we harvested early. Got tillage done early. Heck, you guys were doing recreational tillage. You're just tilling stuff because you could, because the soil were fit. Bean stubble got ripped. That hadn't happened in a long time. A fall where we actually mineralize nitrogen. So the microbes are breaking residue down. Microbes require three things. They require a little bit of nitrogen, they require heat, and they require moisture. The hotter the fall, the more residue is going to be broken down ahead of spring. So we actually had a net nitrogen fall. Soils were mineralizing nitrogen when we got all said and done. And so the difference between a mineralized nitrate nitrogen and the fertilizers we use is mineralized nitrogen is 5 times more soluble. It's going to get into water about 5 to 7 times faster than any fertilizer we use. And so all that nitrogen that we mineralized last fall, that's what they're finding in the lakes. It moves real quick and easy. So they probably found some DAP in there, but they have not found, in my opinion, much of our anhydrous ammonia in the lakes. And so about any time I give a nitrogen talk, I always put this graph up here. It's one of my favorites. On the bottom, we have days after emergence. These are just real generic. In general, corn's up and out of the ground before it matures for around 120 days. That differs with maturity, but it's generic. You got your crop stage right here. V stands for a collar. So we call a collar when you have a leaf out there and it fully attaches to the stem and it makes a little seed. Okay? That's a collar. So the leaf sticking up out of the top that hasn't quite attached, we don't count that one. So V6 corn in general is going to be probably in between boot and knee high, depending on how tall you are. V12 corn's probably generally, I'd say mid-chest high. V18 corn, depending on the varieties, probably 12 to 15 foot tall. And the R stages count for reproductive stages. So you have your blister, or your silk, your blister, your milk, your dough, your dent, your black layer. On up, black layer is R6, or maturity. Then you have the percent of total uptake here on the left. And then the colors represent where it goes. So this is the amount of nitrogen that gets built into leaves. This is the amount that goes into the stalks, cobs. And then the yellow portion is what actually goes into the grain. What we can grind up and find in grain when it's all said and done. Big kicker to this is when you look at the first 40 days of growth. So from emergence all the way up to about V10. So, I'd say that's up in here on me, V10. 15% of your nitrogen. That's it. 15% goes in the first 40 days. I mean, that's not very much when you think about how long the corn's been growing and how big it is at that point. The second 40 days is the big pull. Okay, that's 65% of your nitrogen's going up in the second 40 days. In our 200 unit example, that's 130 units go up in the same 40-day time frame, but from about V10 on up to the blister stage. This example, it just shows how corn transitions from what we call standard growth into the rapid growth phase. Anybody ever heard the term growing degree units, GDUs? Okay, that's thermal time for corn. And it has to do with the high and the low of the day. So corn puts on a leaf about every 85 heat units. from emergence to 10 collars. About 10 collars, the plant's going to find another gear and start growing faster. And so from 10 collars to tassel, it puts on a leaf every 50 heat units. You guys, in June, Central Illinois, we can pile on 30 to 35 heat units a day in June. That's a leaf every day and a half. I mean, that's explosive growth. That's the rapid growth phase. And that's why at this time, right here to this V10 area, it just blows off. So if you don't have adequate nitrogen during that stage, the plant's taking 6, 7 pounds of N up per day some days. I mean, it is rapid and it's aggressive. So you got to have your nitrogen in a usable form and not too deep or leached out, or it's going to starve to death. And then this last 40 days, still have 20% of your nitrogen to go in. First time I saw this, I thought it was crazy. So I got 15% that's going to go in this real lush plant that's up to my waist. But after I've tasseled, I got 20% that's going into the grain. So the corn plant isn't done with nitrogen once it gets fertilized and tassels. I mean, it's still actively taking in nitrogen. Best way to think about nitrogen uptake is like a bottle rocket. You light the fuse down here and it takes a long time for something to happen. Then it shoots off and explodes. That's about as good a correlation as I've ever found to talk about it. So a season-long feed is really important. Generally up here, we get blessed with mineralized nitrogen carrying our last 40 days of growth. You know, good organic matter soils. Sometimes they'll show us a response to side dressing. Sometimes they won't. You go into Mason County, timber soils and Cass, loamy river bottoms. Generally, we're not blessed with getting 70, 80 pounds of N released out of the organic. So I'm going to move to a few nutrients I guess I got on my watch list. Sulfur is a big one. I think Ashland here moves a lot of ammonium thiosulfate and sulfur. They recommend it a lot. One of the big things about sulfur and why we're starting to find it now came from two reasons. Y'all are growing better corn and the Clean Air Act. Two main reasons. So at the bottom here, I got the deposition maps of sulfur that we used to get out of acid rain. We were burning high sulfur coal from southern Illinois and the eastern seaboard. You know, red was bad to the EPA. It was green for farmers because we used to get, 25 pounds of sulfur deposited out of the air. It wasn't enough to burn you acid rain, but it was enough to feed a crop. So back in the mid-'80s, growing 150 bushel corn and getting 25 pounds through the air, we'd never even thought about using sulfur. The Clean Air Act came along, and this is what it looks like in 2012 and 2014. You're only going to get about 8 to 10 pounds out of the air now. And instead of raising 150 bushel corn, we're raising 240 bushel corn. 250 bushel corn. I mean, 200 bushels is a crop failure for some of y'all anymore. Bushel of corn is going to take off about 0.8 pounds of sulfur per bushel. So you got looking at a 240 bushel corn crop, it's going to take off around 20 pounds of sulfur, and you're only getting 8 through the air. That's why we're starting to see these responses. You couple in the fact that a lot of sulfur is mineralized just like nitrogen from the organic matter. So you definitely want to target sulfur on your lower organic matter soils. That's where you'll see the first response, but we feel like we're seeing a response in all soils. The other key part about sulfur is what kind of charge is it carrying? Negative, just like nitrate. You leach sulfur just like you leach nitrate. Actually, you release it worse because it carries a higher net negative charge than even nitrate did. So it's volatile with water just like nitrate is. We recommend, if you like using sulfur, we like to use ammonium thiosulfate. It's a 12% nitrogen, 26% sulfur blend. And the reason we like to go with ammonium thio is it's got two forms of sulfur. It has, some of it is elemental sulfur, which is basically slow release, kind of like the old rock phosphate. It's going to release slowly over time. And then some of it is immediate sulfate sulfur, which the crop can use pretty quickly. Because it has that blend, it also acts as a nitrogen stabilizer. And so we typically like throwing ammonium thiosulfate in with 28% when we're doing the 28 with the chemicals, because it'll help stabilize the 28 from blowing off. You know, putting that urea on top of the ground, it helps stabilize it a little bit. So we tend to tandem those mixes together, both for crop needs and for nitrogen stabilization. Boron's been a big one, has been for the last several years. Big reason why we're seeing huge boron deficiencies for several reasons, but you know, look at our charge on boron, the boron that goes into the plant. That carries a -3 charge. It is the most soluble, leachable, lossable, I don't even know if that's a word. It's going to go away real quick. How about that? Boron goes away really quickly. And you know, when we start taking tissue tests, boron just shows up more and more and more in a lot of our tests. And a lot of it, I think, has to do with the change in hybrids over the years. The U of I actually redrew some of their nutrient uptake charts. So this is the same thing that we looked at for nitrogen. Growth stage on the bottom, percentage on the pounds on the left. You know, look how much boron's going into the plant right ahead of tasseling. There's a real good reason for that. When you think about boron, it's all about reproductive growth. Tassels, pollen, silks, and ears. That's where the majority of the boron goes. And then you have a significant portion of boron that goes into the grain. And these charts changed a lot from when U of I first built them back in the 70s and 80s. They've redrawn a lot of these. And a lot of it has to do with the germplasm. And so I'm an old corn breeding nut from way back. But, you know, 20, 30 years ago, we were all pretty much planting the same hybrid. I mean, there were little wrinkles here and there, but it was all pretty much the same stuff. It had big white leaves, it had flexible ears, it had chaffy grain. You know, it all went down. There was a reason it was all pretty close together. And so when U of I made their charts for those type of varieties, they were all pretty similar. Well, back in the late 90s, early 2000s, you had folks like Monsanto going down to Brazil and buying germplasm. They were going to China and buying germplasm. Pioneer was buying stuff from South Africa. We've introduced all these foreign genetics, and they're different. You know, a lot of differences in hybrids. They're mutts now. They might have a 10% blend from Brazil and 20 from China and so on. But what we failed to do as agronomists and researchers, we failed to really think about the environment where we pulled those hybrids from. You know, you look at Brazil, they have zinc toxicities in there. You know, we're starting to see zinc be one of those nutrients that is on a watch list. You go to South Africa and the soils are really acidic. They're red. So we bring all these things back. Bottom line is our nutrient patterns have changed. And boron is one of those big ones. Sulfur is huge. Look at how much sulfur goes into the grain fill. Anybody ever even consider sulfur being part of grain fill? We always thought it just made the crop green. You know, a tassel on sulfur, you're only 55% done. Boron. You got all this boron going in here to build the tassels and go in the grain. It's the differences in cycles. Zinc's another one. Zinc is shown really common in tissue tests that are coming back. And the thing about it is zinc's pretty stable in the soil. It's going to carry this +2 charge and make a real stable bond there. But I think our hybrids are liking more zinc than they did 30, 40 years ago. And I think zinc is a bigger component of grain fill than we ever considered. Here are those same charts from U of I here. Look where we're at tassel time. 50% done with zinc uptake. Look at all that blue area, that's the grain. That's how much zinc's going into the grain. There's this tremendous curve that starts at grain fill where zinc's starting to fly into the plant. Just a lot of different things that we see with some of these microbes. A lot of you will put zinc in with starters, and that's a really good idea because zinc helps phosphate become more efficient. They have a synergistic relationship. So anytime you concentrate phosphorus, you're tricking the plant into thinking it's probably got 100 pounds of P on there at one point. That can almost be toxic. If you put zinc in there, it helps both those products be more efficient. They work synergistically together. So zinc's one to watch. It's stable in the soil, but the problem with zinc is we like to use EDTA mixes because they're more stable. They have metal elements that surround the zinc in that solution. So like the red label zinc that we sell here, it's got metals that surround that zinc so that the soil doesn't fixate it. So a quart per acre is real easy to use with a starter or a 2x2 band because we're concentrating it. We can use a quart. That's what, $6.50, $7, Bill? Yeah. To broadcast it, to treat the whole soil, we probably need to be using a gallon and a half, and then the cost just outweighs the benefit. That's the big issue with zinc. You got to band it in small areas next to the plant. A lot of the things I just talked about, we tried to replicate at the research farm. So nitrogen and banded applications. That's what we were looking at. Here's what the farm looked like. I want to put this up here because there's been a lot of questions on corn. You know, why was the corn on corn so much further behind the bean stubble this year? I think a lot of us felt that. These are our graphs comparing first year corn in the red to corn on corn in the gray. And they've been doing these over there since about 2007. What you'll notice just at a quick glance is sometimes the bars are wider than others. So look at this gap in 2010 versus what we saw in 2013. You know, everything came back around. Corn on corn is kind of a mystery to a lot of people. They don't understand why and how. And I'm one of those people. But the one thing I do know with corn on corn is it is always set up by your previous year's harvest. So if you pick early, you get your tillage done early, you have a warm fall, and you don't rut the ground up, it's usually a really good year the next year to grow corn on corn for a lot of different reasons. But your soil microbes that decompose residue, they have to have heat to decompose this residue. And so if you have a cool fall, you're left with all the residue left in the spring. Microbes require nitrogen to break down residue, so they're going to steal it from you. In a warm year, we get some of that decomposed before planting time. So if you just look at this chart, it lines up really well. Was 09 a very good harvest? I mean, it was cold. I remember four-wheel drives pulling combines, picking corn in the fall of 2009. It was cold, it was wet, a lot of it was finished in December. Virtually no tillage done. It was one of the worst falls we've had in a long time. Look at the gap that you see the next year in corn on corn versus rotated ground. It's huge. I mean, the ground wasn't ready for corn on corn. It wasn't set up. In comparison, 2012. Harvest 2012, we were done by the 1st October. It wasn't because we wanted to be there, we just wanted to get corn picked. It's hot. It's one of the hottest falls we've ever had. Again, we did recreational tillage. We got the ground prepped well. Everything was tilled in. Look at the corn on corn gap in 2013. It's virtually non-existent. So early falls help set up good corn on corn. With that being said, I anticipate very good corn on corn yields in 2016. The soils are prepped well. We did a nice job last fall. We picked early. We had the heat we need and we got some moisture. So just to put some numbers in perspective, I said that microbes require nitrogen to break down residue. And they're going to steal it from an actively growing corn crop. You know, a 200 bushel corn crop is going to need about 127 pounds of N for the microbes to get all the residue broken. That's a huge number if you're growing corn on corn. These are the bugs that get that done. You got fungi, you got bacteria, you got earthworms, you got actinomyces. You know, all these things help break your residue down. On a side note, these actinomyces, you may like how dirt smells after you work it. It smells really good. You smell the microbes. Those are actinomyces microbes that give off that odor when they hit oxygen. Kind of a side note for a soil nerd. But when we look at corn on corn versus bean stubble, we put things in what's called a ratio. It's a carbon to nitrogen ratio. So it's C to N, carbon to nitrogen, and it's basically how much residue you have versus how much soil available nitrogen that we anticipate. And so we got some numbers out here. So corn on corn is a 65 to 1 ratio, whereas you look at bean stubble, that's about 30 to 1. Makes sense, you got a lot less residue. Microbes that break residue down are looking to get to the 20 to 1 number. So anytime you have more residue, like wheat or corn stover, we're immobilizing nitrogen. Immobilization is a fancy term for microbes stealing it from your plants. They're taking nitrogen to break residue down. And they are going to do that until they get to a 20 to 1 ratio. The term soybean credit is probably the worst term that our universities ever could give us. There's not 30 units of nitrogen left over by soybeans that the corn gets. It just takes 30 more units of nitrogen to get this decomposed. So it should have been more of a corn on corn penalty than a soybean credit. You need 30 to 40 more pounds to break the residue down to get down to 20 to 1. So the trick is, for corn on corn in general, to get that number as low as possible before you plant, before the crop starts growing. More of the residue we can get broke down in the fall, the better off we're going to be, because it's less that they're going to steal from the plants in the spring. So good falls help with that. We should have really good mineralization. This is probably my best example on nitrogen immobilization. I was working up by Peoria one day and I saw this, and I had the farmer with me. I said, "What in the world was that?" He said, "Well, I broke a big old bale of wheat straw right there, and I was too lazy and I just spread it out and worked it in." That's what the corn looked like where his wheat straw was. He probably had a carbon to nitrogen ratio of 500 to 1. He put 600 pounds of nitrogen on that spot with urea, and the corn died. It never grew. You just can't get enough nitrogen. There's too much residue. They're just constantly taking it from you. That's immobilization. So we wanted to go out to the farm this year and test some things, and we wanted to look at, could we influence some of this corn on soybean, nitrogen inefficiency early. Let's just call it inefficiency. So we wanted to test banding or broadcasting. Ed Varson was my soil professor at Southern Illinois. Old Ed, and we called him that because he was old. Ed went down there. I think he was old when Ed was there. The guy farted dust. But his famous saying was, if you want to keep something around with fertilizer, you put it in a band. He said when you band a fertilizer, you concentrate it, and you limit its exposure to microbes that are breaking things down. He always used to say it'd be like filling up a small trough of diesel fuel and lighting it versus spreading it all off on the ground. You know, that where it's concentrated is going to burn for a lot longer. So we wanted to test that theory, banding versus broadcast. We wanted to use nitrogen because banding P&K just really isn't feasible for how we all operate. I mean, it's just, you could try it, but a lot have and they don't do it anymore. Banding versus broadcasting. Basic concept is when you band it, you're trying to feed the plants. When you broadcast something, you're feeding the soil. You're feeding these microbes that are taking 127 pounds to decompose your crop. You concentrate it. Now, with that being said, I'm not saying that putting 15, 10 gallon to 28% in with your chemicals is a bad thing. It is not. That is a really good way to provide shallow fertilizer to young plants that don't have big enough roots to find your ammonia. You know, if we had compared nothing here to broadcast, we'd probably seen another 10 bushel stair step down. This banded application is just what we're thinking about might be the next step. Some of you aren't going to put liquid on your planters, and that's all right. Stay doing the broadcasting. We're not saying that's bad. Took this theory over to a bigger area, the area to the west of the smaller research farm. And these are bigger trials, 20 to 25 acres. This is the fall ammonia here, spring ammonia here, and then this is our banding theory again. We banded 210 units. with the planter, our 7-gallon of 28, 3-gallon ammonia thiosulfate, could we influence a lot of nitrogen at varying rates with just a little bit of starter? And so we took our little 4-row Prepicator bar, which they don't make anymore for good reason, but these are all 4-row strips, so 300 pounds in, 250, 200, 100, 0. This is corn on corn, anhydrous ammonia planted right back in the strip. So then we turned our starter unit on and just did 25 units in. That's the difference you can make with shallow nitrogen with young cordon seeds that don't have roots big enough yet to grab any in. That's the difference you can make with either your broadcasted 28 with the chemicals or your banded with the plant. One of the coolest things about this whole study to me was, and I'm kind of preaching to the choir here because you guys are strip tillers, this 0 application, we got a 4-row bar. I should not be able to tell where row 1 and where row 4 are. Row 4 has 300 pounds of nitrogen 30 inches away, and it never found a dropper. You can count all 4 of those rows. Never found it. I think we, and myself included, I always talked about anhydrous ammonia being this reaction that was like a basketball down in the ground. You know, it was just, it would gas out and react to nitrogen zone this big. Thinking maybe it's more like a softball instead of a basketball. That nitrogen doesn't move as much as what I have ever given it credit for. So what it prompts me to tell people to do is, you know, when you're out there putting on gas, you strip tillers do it very well. You plant right on top of the strip. But why couldn't we do that with conventional tillers? Everybody's got, not everybody, but most everybody has guidance. You know, I think it is just important for us to save our anhydrous ammonia line that we're putting gas on, even if we're in chiseled fields. Let's try to get those plants right on top of the band of gas. We're doing it anyway. We're out there. It's easy to save your line and bring it back up and plant with it. We ought to be doing that. And then probably the coolest thing about this whole plot was, everybody see this big green line here? That was where this trial was last year. So that green line that you see is 300 units of nitrogen applied in November of 2013. And you could still see it on waist-high corn. So is it all even? Did we lose all of our nitrogen all the time? Absolutely not. When you concentrate something in the band, you increase the longevity. The other thing that happens inside of that band of ammonia, initially when you put on gas, you're going to kill microbes. There was a big push there several years ago for we shouldn't be using anhydrous ammonia because it's not healthy for the soil. What we can do now is we can send in what's called a soil health test. And they pull out how much bacteria and all that other stuff's in that band. Microbes thrive with fertility. They thrive with nitrogen. They seek out nitrogen. And so you initially kill them. But once that ammonia band softens, we actually find higher levels of soil microbes inside the band of ammonia than we do outside of it, because they're looking for the nitrogen. So in that band, you not only concentrate the fertilizer, but you're creating somewhat of a microclimate for better soil microbial activity.